Good morning, everyone. I hope you had a great weekend and everybody's doing great this morning. Welcome to the final week of this little journey that we've been on. Today what we're going to be looking at is half-life, and this lesson can be found on page 34 of your current lesson handout. So if you had a sample of radioactive material, let's just pick on polonium-210. We've learned that polonium-210 undergoes alpha decay. And what we've been focusing on is a single nucleus of polonium-210. And we've learned how to write the alpha decay equation for polonium-210 undergoing alpha decay. But what we haven't really talked about is the fact that when you have a chunk of polonium-210, not every nucleus undergoes alpha decay at the same time. Some nuclei will decay now, some nuclei will decay 5 minutes from now, some nuclei are going to decay 5 days from now, and even 5 years from now. So what determines whether a particular nucleus in polonium-210 undergoes alpha decay or not is something called half-life. And it turns out that in a given period of time, and each isotope in the universe has its own period of time, and we'll talk about that in a second. It turns out that over a given period of time, the probability of a particular nucleus decaying is exactly 0.5. Now in mathematics and science, we don't like to use percent for probability. We like to use either fractions or decimals. But I think it's worthwhile to mention to you that when we say the probability of some event happening is 0.5, what we're talking about here is a 50% chance. So in this period of time, which is called the half-life of the radioactive isotope, each nucleus has a probability of 50% or 0.5 of decaying. And what that means is that if you wait that period of time, whatever period of time it is, you would expect half of the nuclei to have decayed. So the half-life of a radioactive sample, and this is the most important part of what we're talking about today, is the period of time it takes for 1/2 of the sample to decay. And you learn about this type of change in Math 30, we call it exponential change. Specifically, it's a type of exponential decay. Now the warm-up is going to introduce us to this idea of half-life and what it means in terms of radioactive decay. So carbon-14 is a particular isotope of carbon whose half-life is 5,730 years. We've talked about this in the past, but the symbol A in math and science means years. And we're assuming here that initially we've got a sample of 100% carbon-14. We're asked to complete the table below. So at the beginning, when 0 half-lives have elapsed, which means that the age of the sample is 0, there is 100% of the carbon-14 remaining, because none of it has had a chance to decay yet. If we wait 1 half-life, which is 5,730 years, what we would expect to happen, and what does happen, is that you only have 50% of the carbon-14 remaining. If we wait an additional half-life, which will take the running total for the age of the sample up to 11,460 years, 11,460 is 2 multiplied by 5,730. What you're going to expect, and what we do observe, is that only 25% remains. So each time an additional half-life goes by, we are left with 1/2 of what was there at the beginning of that additional half-life. So if we wait another half-life, we get half of 12.5%, and that works out to 6.25, and half of 6.25 is 3.125%. Now we're asked to compare the amount of material that decays as time goes on, and essentially the answer to this question is that as you wait a longer and longer period of time, less and less will decay. In the first half-life, 50% of the sample decayed, and in the second half-life, only 25% of the sample decayed. And the explanation for that is that if there is less material there that can decay, there will be less material that does decay. In order for us to visually take a look at what this means, we're going to look at a graph showing the percent of carbon-14 remaining as a function of the number of half-lives. And we start off with 100%, and after one half-life, you're at 50%, and then you're at 25, 12.5, 6.25, and then 3.125. And the curve looks like that. This is what we call an exponential curve. There's a formula that we've developed in this course to use to describe what's going on here, and it's on your formula sheet. I'm not sure why they were fixated on the letter N here when they had all other letters of the alphabet to choose, but this equation has 3 N's in it. Capital N is the amount of material remaining. So in our example in the warm-up, we were talking about the amount of carbon-14 remaining. N0 was the initial amount of the parent material, carbon-14 in this case. So in our warm-up, N sub 0 would have been 100%. And lowercase n is the number of half-lives that have elapsed. Now the amounts in this equation, the capital N and the capital N sub 0, could both be percents, they could both be kilograms, they could both be numbers of nuclei, or they could be what we call activity. And what activity is how many decays are occurring each second. The unit of activity is called a becquerel. So it doesn't matter what units you choose for N0 and capital N. What's important is that you have the same unit of measurement for both. The number of half-lives, which is lowercase n, could always be found by taking the total time elapsed and dividing by how much time one half-life is, which is called the half-life of the material. I suppose if you ever wanted to find out the number of half-lives, you could as well use a ratio. This formula, n equals T over H, is not on your formula sheet. Let's take a look at a couple of examples. A radioactive sample of polonium-210 undergoes alpha decay and the half-life is 138 days. What mass of an original sample of 40 milligrams will remain after 1 year? So let's make an itemized list of everything that we know here. We're told that the total time is 1 year, so we should know that that's 365 days. You're told the half-life of the radioactive sample is 138 days. And the initial amount, which is N sub 0, is 40 milligrams. So our formula is N, the amount remaining, equals N sub 0 multiplied by 1/2, or 0.5, raised to the lowercase n. Now, lowercase n is the number of half-lives that have elapsed. And we can figure out how many half-lives have gone by taking the total time, 365 days, and dividing by how many days one half-life is, which is 138 days. And this is going to give us the number of half-lives. 365 divided by 138 gives 2.64 half-lives. So we can start putting things into this formula. The amount remaining will be N0, which is 40 milligrams, multiplied by 0.5, raised to that 2.64. So it's a pretty straightforward calculation. All we have to do is load those numbers into our calculator. 40 multiplied by 0.5 raised to our answer gives about 6.4 milligrams remaining. And that's example 1. All right, number 2, in living tissue, the activity of carbon-14 is 0.23 decays per second, or 0.23 becquerel. I don't want to get into a lot of detail here because it's probably not necessary, but as long as the organism is alive and experiencing cellular respiration, there's an exchange between the organism and the environment of carbon-14 that keeps the carbon-14 level at 0.23 decays per second. As soon as the organism dies, then there's no longer that exchange of carbon-14, and the carbon-14 activity within the organism starts declining. So if we measure the activity of some sample that was previously living, we can compare the activity that the sample has now to the activity that it would have had when it was living to determine the age of the sample. Again, let's make an itemized list here. We've got the half-life this time is 5,730 years. The initial, I don't really want to call it the initial amount, but in our formula I've told you N0 is the initial amount. This is really, in this case, the initial activity though. It's 0.23 becquerel. The activity at some point in time later is 0.0018 becquerel. And you're asked to determine the age of the sample. So when we look at our formula, we have n equals n sub 0 times 0.5 to the lowercase n. What we need to know is what lowercase n is, because if we know what little n is, then we know how many half-lives have elapsed since the organism died, and that can be useful in finding out how old the organism is. So let's load these numbers in. You get 0.0018 equals 0.23 multiplied by 0.5 to the n. Now how are we going to solve this? We're going to start by dividing both sides by 0.23. And that gives us 0.007826. Equals 0.5 to the n. I'm pretty sure everybody who's in this course now has taken logarithms in either Math 30-1 or Math 30-2. And the only way that you're going to mathematically solve this equation is by taking the logarithm of both sides. So we can have log of 0.007826 equals log of 0.5 to the n. Those of you that are in calculus, feel free to take the natural logarithm of both sides. As long as you are consistent in the base of the logarithm that you use, it's not going to matter. So you could write, for you calculus people, ln of 0.007826 equals ln of 0.5 to the n. Of course, we do this because there's a property of logs called the power law, which says that you can move that power out in front. What that allows us to do then is to solve for that power. All I have to do to find n is take the logarithm of 0.007826 divided by the logarithm of 0.5. And that's going to give us the number of half-lives, which is not quite the answer to the question. It's giving us 6.997. And by the way, I just want to show you calculus people that you're going to get the same result. If we would have taken 0.0018 and divided by 0.23, and instead of taking the log of that number over the log of 0.5, you took the ln of that number divided by the ln of 0.5, you still get 6.99749. You get the exact same number of half-lives. Now we know the number of half-lives. And then to find the age of the sample, I know that a lot of you will just want to multiply that number by 5,730 years because that's how much one half-life is. But if you were ever unsure, of course, what you could do is you could say by way of a ratio, 5,730 years is 1 half-life. That has to equal x years over 6.997 half-lives. And when you cross multiply, you can see that you're going to have to multiply that 6.997 by the 5,730, and then we will have our answer. The age of the sample is approximately 40,000 years old. And that's it. Very, very short lesson. There are some problems listed. These are the problems on the following page: 1, 3, 5, 7, 10, and 12. Any other problems are optional. We have one more lesson we're going to be covering on Wednesday. And it's going to be looking at the properties of fission and fusion, and then we will be done with the content for the course. Don't forget, your final assessment is due Friday. By the way, you should have all of the tools necessary to complete the final assessment already. I've taught you all of the concepts at this point in time. So have a fantastic rest of the day. We have a brief Google Meet tomorrow at the beginning of period 1 for about the first half hour to 40 minutes or so. I will be there. And if you need any help outside of that time, please send me an email and I'd be happy to help you out. Have a fantastic rest of the day, you guys. Work hard this week and then you can relax next week. Okay? You take care of yourselves. Talk to you later.